Hello everyone, welcome to the first video of Module 3 for ME 215. So this section of the course is called Control Volume Analysis, and there's a real connection between control volume analysis in fluid mechanics and open system or control volume analysis in thermodynamics from last term. So this video is going to introduce control volume analysis and develop something called Reynolds transport theorem. And we'll talk about why we need Reynolds transport theorem in a few moments. So just by way of an example, let's say that we have an airfoil. So there's airflow over top of this thing from left to right, and we're interested in the forces generated by this airfoil. So in general, those would be lift and drag forces, but we'll just keep it general now and just say we want to know what force does the air exert on this object as it flows over top of it. Well, there are two general approaches we can take to this analysis. If we wanted to use a control mass, then one way we might go about doing that is to identify a control mass upstream or in front of this airfoil. And remember what a control mass is? It's an identified piece of mass. So the mass of air inside of this black line is always the same. Air is not allowed to cross that solid black line. So this air has some pressure and some velocity in some direction. So what we could do is apply conservation laws to that control mass and follow it or study it as it flows over top of this airfoil. So if we look at this control mass a little bit later, we could use those conservation laws to figure out where it moves to, how its shape perhaps changes a little bit, and how the pressure of that control mass changes. And we could follow it all the way over the top surface of this airfoil as it moves and deforms and until it leaves the back end of the airfoil and heads off downstream. Now, what would we learn by doing that? Well, we would learn something very important. Remember, our objective is to calculate the forces on this airfoil. So if we studied that control mass as it moved over top of this airfoil surface, one of the things that we could learn is the pressure distribution on the top surface of this airfoil. So we would figure out what is the pressure everywhere on this surface of the airfoil. Well, in the last section of the course, we learned a technique where we could take a pressure distribution on a surface and figure out a force or even a moment from it. So we would actually then go and use exactly the same equation that we used in the fluid statics portion to get a force or a moment, only instead of using the basic hydrostatic equation for the pressure in that integral, we would have to use the conservation laws that we had applied to this control mass flowing over the top surface. Now, clearly, in order to get a full picture of the forces, we would also have to study another control mass flowing over the bottom surface. So that control mass approach would give us a detailed pressure distribution on the top and bottom surface of this airfoil, which we could then integrate to get a force and a moment if we want both of those. So that's one way to do this. However, in this course, we're not going to take that approach. Instead, we're going to do a control volume analysis. So how would we approach a control volume analysis in this same scenario? Well, we would first of all draw a control volume around the thing we're interested in studying. And in this case, the thing we're interested in studying is this airfoil. So I've drawn one possible control volume around this, and that's just a box surrounding the airfoil that we're studying. Now, in a control volume analysis, we don't go inside and look at the details of what's happening in the control volume. Instead, we're interested in what's happening on the boundary of the control volume. Now, this particular control volume is just a box. It's a little bit oversimplified, and we'll look at a more sophisticated version of this in an example later on. But to a first approximation, the things that are important that are happening on the boundary of this control volume are happening here, where we have an inlet, so there is air flowing into our control volume here. Notice the big difference between a control volume and a control mass is for a control volume, we can have mass crossing our surface, and here we certainly do. There's an inlet here. As long as this line is far enough upstream, then that's just a uniform inlet. That's just the wind or the air velocity approaching this airfoil. So we have a uniform velocity at the inlet. So the air comes into our control volume, it interacts with this object in some quite complex way perhaps, but eventually it leaves the control volume. So if we were to look at this exit of the control volume, there the velocity profile might look like this. It's a little bit faster up here, immediately behind the object it's a little bit slower, and then again might be a little bit faster down here. So there's a different velocity profile entering and leaving this control volume. Now in reality there might be a little bit of stuff happening at the top and bottom of this control volume as well, but there's a way to account for that also. I don't want to make this too complicated yet. Now, what do these velocity profiles tell us? Well, the way a control volume analysis works is it ignores essentially the details of what's going on inside of here. Instead, if we were interested in the force on this object, one way we can get at that force is by looking at the momentum that this fluid has at the inlet and the momentum that the fluid has at the exit. And the change in momentum that that fluid experienced comes about because there was a force exerted on that fluid while it was inside our control volume. So if it has a different momentum leaving than it had coming in, there must have been a force exerted on it in the control volume. And in fact, the force exerted on the fluid happened because there's an object in there. So we can look at the changed momentum at the inlet and the exit, and from that figure out how much force was exerted on the object inside the control volume. So that's how control volume analysis works. It forgets about the details inside. Instead, it identifies a control volume, looks at the properties coming in and the properties leaving, in this case momentum, and from that figures out what the force inside of the control volume had to be. So that's the way we would do a control volume analysis to calculate the force on an object like this. So what we need to develop in order to be able to do this is conservation equations that work for a control volume. So the reason we're going to do this is that many problems, such as I've illustrated here, can be more convenient to analyze using a control volume approach as opposed to a control mass. So the problem we have though, the reason we can't just immediately start to do this, is that the laws of mechanics are typically expressed for a control mass. Usually when we pull the laws of mechanics out of our textbook, they're expressed for a control mass. So conservation of mass, conservation of linear momentum, conservation of angular momentum, conservation of energy, these things are valid when we apply them to an identified chunk of mass. And we need to be a little bit careful when we're applying these equations in a situation where there's stuff coming and going out of our control volume. We need to do some extra things to account for that stuff coming and going out of our control volume. So we're familiar with this problem from thermodynamics when we looked at open systems. Remember conservation of energy, which is one of our conservation laws here. When we have things entering and leaving our control volume, we need to account for the energy that they're transporting or carrying with them as they enter and leave. So you'll recall that our conservation of energy equation for a closed system, Q minus W equals delta U, is much simpler than conservation of energy for an open system where we had those extra terms accounting for energy coming and going. Well, it's exactly the same thing is going to be happening here, only the quantities we're more interested in this class are mass, linear momentum, and angular momentum. We will revisit conservation of energy, but only at the beginning of the next module. This module is going to concentrate on these quantities. So in order to overcome this problem and get equations that apply for a control volume, we need to consider something called Reynolds transport theorem. And so this is the solution to this problem, and it's what allows us to express our conservation laws in a control volume form. So in the next video, we'll go through Reynolds transport theorem and develop it formally. So we'll see you there.